preparing to live stream. It's
Yeah. Now, can you please make me host again? And
okay. I can't see participants. Yeah, you are host now, Soumya.
Yes, sir. Let me start the recording.
Yeah.
Yeah, we can start.
Professor Sharma.
Yes, sir.
आपके 10 मिनट टेक्नोलॉजी ने खा लिए हैं.
No problem. But altogether, how much time do I have?
You tell me how much you need. Accordingly, we can go ahead about it.
What is your suggestion?
Right. 1 घंटा तो चलेगा, ठीक है?
हाँ, ठीक है. 1 से 1.5 घंटा. Is it okay?
Yeah. With the questions and. So let me formally begin. Yeah. So welcome all to this session of Math Clinic. It's a session on very important and very basic topic called linear algebra and its applications. And I'm happy that Professor Rajendra Kumar Sharma from IIT Delhi has agreed to deliver his thoughts on this topic. Professor Sharma was, after his PhD, he joined IIT Kharagpur and then later on joined IIT Delhi. He has been there for about 33 plus years and almost equally number of PhD students he has guided, about 34, more than 80 MTech projects, and he has over 155 research papers in reputed international journals. He has participated in international conferences and visited countries like France and Germany as postdoctoral fellow. So I think without to spend, his field of interest is algebra and cryptography. So that is important. And let me request Professor Sharma formally that, sir, welcome to this Math Clinic talk, and please.
Namaskar, Professor Anna, for your sweet, kind words. I'm very, very grateful to you. And of course, I'm extremely delighted to meet you and all other people, of course, from a distance. I love meeting people and shaking hands with them. In person, of course, but nowadays, as we can see, this is the next best possible scenario, that at least we are able to see each other, though through a screen. Anyway, whatever is possible, we must try to make a good use of this technology. Of course, in 10 minutes, as Professor Anna has said, that we have lost in the process of setting up, but I hope it's still good enough time to go beyond that. So, well, sir, as far as mathematics is concerned, it's a wonderful subject. It's very fascinating, very challenging. And it's very rightly said that mathematics is the queen of all sciences, because if mathematics is strong, all sciences, of course, develop and prosper like anything. And in our ancient literature, Vedas mein bhi kaha gaya hai, yatha shikha mayuranam naganam maniyo yatha tadavedanga shastranam ganitam dhanmustite. And as you all know Sanskrit very well, but still for my sake of happiness, I would say that Yathashikha Mayuranam, as on the crest, as there is a crest on the head of the peacocks, so as is the gem on the head of a cobra, the snakes. Tadavedanga Shastranam Ganitam Mudhana. The same way mathematics sits on the top of all sciences. The meaning thereby is this is the address of mathematics, that it occupies the top position among all sciences, as its applications also show the same. Well, as far as mathematics is concerned, of course, is very challenging, but at the same time, I also would say that history is very fascinating. And history of every subject, be it sociological history, geographical, or anything, and in particular, since I am interested in mathematics a little more, so history of mathematics and the development of subject is also very fascinating. So I would just say a few words about the development of the subject called linear algebra. And let me share the screen now so that we all can see the same. And please confirm if you are able to see the screen so that we know. Are you able to see the screen, gentlemen?
Yeah.
Okay.
Yeah, we can.
So thank you very much. So we shall be talking a little about system of linear equations, matrices, vector spaces, etc. in the context of linear algebra and a bit of applications. Well, linear algebra, as we all know today, is the branch of mathematics concerning linear equations, linear mappings, their representations, vector spaces through matrices, and is a central theme to almost all areas of mathematics. It's, for instance, fundamental in modern presentation of geometry, including defining the basic objects such as lines, planes, rotations. Is used in physics, chemistry, architecture, electrical engineering, computer science, and so on. Nothing is left actually which does not have its roots in mathematics, and in particular linear algebra, because it allows modeling many natural phenomena and computing efficiency with such models. A brief history of the subject called linear algebra and matrices. Of course, there are several ways of going back to the history. One is through matrices, another is through equations, another is through geometry, and so on. Well, there is no unanimity actually when the subject can be said that it was born. Yet, a bit of pieces that I have collected from the literature says that the study of system of linear equations were first introduced by the Babylonians, and that was around 1800 to 2000 BC. So around say 4,000 years ago, the people of Babylon knew how to solve a simple 2x2 system of linear equations where the number of unknowns were 2. And around 200 BC, the Chinese published the 9 chapters of the mathematical art, and they displayed the ability to solve the system of equations 3x3. So it involved a matrix also of the size 3x3. The simple equations of the form Ax plus b is an ancient question that worked by people from all walks of life. The power and progress in linear algebra did not come to fruition until and unless it was the late 17th century. That's when in Europe it was taken up for a systematic development. And for solving the system of linear equations, Cardan constructed a simple rule for 2 linear equations with 2 unknowns around, say, 1550 AD. Cardan, an interesting and colorful personality, published the mathematics book Ars Magna. And in that book, Cardano and Ilya first used the numbers which were known as complex numbers due to, say, William Rowan Hamilton. Lagrange used the matrices in his work on the optimization problems of real functions around 1750 AD. And some of the mathematicians consider that Lagrange as the founder of the system and was used widely in the context system of linear equations. Also, determinants, the concept was used by Gauss at that time. He formulated this set of errors to be minimized in the system of linear equations. The ancient China, as I said before Christ, it was used different ways of solving systems of linear equations. The solution methods were not fully different from each other, but yes, they have shown that it could be used for 2 or 3 equations with the same number of unknowns. Also, the ancient Chinese made some correlations between the number of equations and the number of unknowns for unique solutions and more than one solution as well. So it appears that there are many examples and applications, problems and solutions in the old textbooks. So history could be that it is quite ancient that way. And the introduction and the development of the notion of a matrix and the subject of linear algebra followed the development of determinants, and that arose from the study of coefficients of systems of linear equations. Leibniz is treated as one of the founders of calculus, and he used the determinants in around 1693. And Kramer, of course, presented his determinant-based formula for solving the system of linear equations. And today we know this method as Kramer's rule, and that was 1750. And in contrast, the first implicit use of matrices occurred in Lagrange's book on bilinear forms in the late 1700s. Lagrange desired to characterize the maximum and minimum determination of functions of several variables, and this method is known as the method of Lagrange multiplier. In order to do this, he first needed the first order partial derivatives to vanish, and additionally required the condition on the matrix of second order partial derivatives held. And this condition is today called positive or negative definiteness. Although Lagrange did not use matrices explicitly, Gauss developed Gaussian elimination around 1800 and used it to solve least square problems. So in celestial computations, and later in computations to measure the Earth and surface. And this subject is called geodesy. Is concerned with determining the shape of the Earth and locating exactly the points on the Earth's surface. Though Gauss's name is associated with this technique for successively eliminating variables from system of linear equations, Chinese manuscripts from several countries earlier have been found that explain how to solve a system of 3 equations, as I just now mentioned, in 3 unknowns. The Gaussian elimination, of course, was the name later on given for more systematic elimination. For years, Gaussian elimination was considered part of the development of geodesy and not mathematics. And the first appearance of Gauss-Jordan elimination in the print was in the handbook on geodesy written by Wilhelm Jordan. And many people believe that it was actually the Camille Jordan in the Gauss-Jordan method, but it was actually Wilhelm Jordan. For matrix algebra that developed so fruitfully, one needed both proper notation, proper definition of matrix multiplication as far as the algebra to start with. So both needs were then met, and almost about the same time and almost at the same place. In 1848, it was in England that Sylvester first introduced the term matrix, which was the Latin synonym for the word bomb, as a name for an array of numbers. Matrix algebra was nurtured by Cayley. Cayley studied compositions of linear transformation. Many times, many people ask for admitting. I think the control can take care of this. So matrix algebra was nurtured by Cayley in 1855. Cayley studied compositions of linear transformations. and define the matrix multiplication this way, so that the matrix of the coefficients of the composite transformation ST of S and T as the multiplication of the matrix for S with the matrix of T. And he studied the algebra of these compositions, including the matrix inverses, famous Cayley-Hamilton theorem. And that states that square matrix is the root of its characteristic polynomial. Characteristic equation by the use of language we treat the same, although it is not. So it was given by Cayley in 1858 to memoir on the theory of matrices. The use of a single letter to represent a matrix was, of course, crucial for the development of the subject. And it was the formula that brought together the relationship between the matrices and the determinants. The formula was that the determinant of AV is the product of their determinants. Cayley wrote that there would be many things to say about this theory of matrices, which would, it seems to me, precede the theory of determinants, quote, unquote. Mathematicians also attempted to develop algebra of vectors, but since there was no natural definition of the product of two vectors, that can be defined in arbitrary dimensions. The first vector algebra that involved non-commutative product, which we call as the cross product V cross W, where V cross W need not be equal to W cross V. And that was proposed by Hermann Grassmann in his book in 1844. Grassmann's text also introduced the product of a column matrix and a row matrix, which resulted in what is called a simple or a rank 1 matrix. In the late 19th century, the American mathematical physicist Willard Gibbs published his famous treatise on vector analysis. In that treatise, Gibbs represented general matrices, which he called dyads. The sum of simple matrices, which Gibbs called dyads. Later, Dirac, the famous physicist, introduced the term bracket for what we call the scalar product of a bra, that is row vector, times a cat, that is the column vector, and the term bracket for the product of a cat times a bra, resulting in what we call a matrix, a simple matrix, as in this sense. Our convention of identifying column matrices and vectors was introduced by physicists basically in the 20th century. Matrices continued to be closely associated with linear transformations, and by say 1900, sorry. So by 1900, they were just a finite dimensional subcase of the emerging theory of linear transformations. The modern definition of a vector space was, of course, introduced by Peano. That was 1888. Abstract vector spaces whose elements were functions were too soon full. There was renewed interest in matrices, particularly on the numerical analysis side of matrices after World War II, with the development of modern digital computers. John von Neumann and Hermann Goldstein introduced condition numbers in analyzing round-off errors in 1947. Alan Turing and von Neumann were the 20th century genius in the development of the stored program computers. Turing introduced the LU decomposition of a matrix in, say, around 1948. The L is, of course, a lower triangular matrix with 1 on its diagonal, and U is an echelon matrix, upper triangle. It is common to use LU decompositions in the solution of a sequence of systems of linear equations, each having the same coefficient matrix. The benefits of the QR decomposition was realized a decade later. Q was to denote the matrix whose columns are orthonormal plus norm 1. So orthonormal vectors, and R a square upper triangular invertible matrix with positive entries on its diagonal. The QR factorization is used in computer algorithms for various computations, such as solving equations and final eigenvalues. We here would like to introduce the notion of systems of linear equations which lie at the heart of linear algebra. So we shall introduce some of the central concepts of linear algebra through the system of linear equations. And as I said in the very beginning, that this is going to be a very, very elementary introduction to the subject, and therefore the examples and the subject also will be kept as you said, as elementary as possible. Okay, so friends, the linear equations. So a linear equation in the variables say x1, x2, xn is an equation that can be written in the form even x1 plus a2, x2 and so on plus a and xn equal to 0. This is a misprint, so this should be actually b. So where b and the coefficients, sorry, this is b actually, this is not 0. Where b and the coefficients even a to n are the real or complex numbers, usually we know them in advance. So the subset n may be any positive integer. When we say any positive integer means it automatically means finite. Just a few simple examples. So the equation say 2x1 minus 7x2 equal to minus 5 is a linear equation. The equation, say for example, 3x2 is equal to 4 times square root 5 minus 2x1 plus x3 is a linear equation because it can be rearranged algebraically after removing the bracket, etc., and writing it properly. So that becomes 8x1 plus 3x2 minus x3 as equal to 4 root 5. Minus x1 plus 3x2, if it is equal to x1, x2, this is not linear because of the presence of the term x1, x2 in this equation. The equation, say 2x1 minus square root x2 equal to 3 is again not a linear equation, as here we have root x2. That is, power is half of x2. A system of linear equations, or linear system of equations, is a collection of one or more linear equations involved in the same variables, to say x1, x2, xn. So one simple example which has two equations here. So 2x1 plus x2 plus 3.5, say x3 equal to 10, x1 plus x2 equal to 6 is a system of linear equations that contains two linear equations. Another example, you can have minus x1 plus 3x2 plus x3 equal to 1, minus 2x2 plus x3 is minus 6, minus 5 x1 plus 7x2 plus 8x3 is equal to minus 8. I'm sorry, here and there might be still some typos, although I tried to correct, but I seek your kind pardon for this same, as here x1 is missing, and this example number, in this example number 2, for example. This solution of a linear system means, say, a list, say S1, S2, Sn of numbers that makes each equation in the system a true statement. That means when you replace each xi by si's, when you substitute, the statements hold. So consider the system of linear equations, say that example just now I stated 2x1 plus x2 plus 3.5 x3 is 10, x1 plus x3 is 6. And you can see that easily that if you substitute for x1 say 8, for x2 say 1, and for x3 as minus 2, both the equations are satisfied, and therefore is the solution of this system, because we see that the values, if for x1, x2, and x3 are replaced by 8, 1, and minus 2 respectively, is to hold correct. So the solution set. Solution set means is the set of all possible solutions of a system of linear equations. Just one example, the same example. So what we see here is that the solution set of this linear system in R, means the real numbers, is 6 minus x3 and minus 2 minus 1.5 x3 and x3, where x3 could take any arbitrary value in real numbers. So this gives you infinitely many solutions, and this set is called the solution set of this linear system of equations in R. Equivalent linear systems. Two linear systems are called equivalent if they have the same solution set. So you can see now here the example just now we have discussed, and the another example is obtained by rewriting this first equation by dividing the second equation written as such. And the first equation is here x2 plus 1.5 x3 is minus 2. These two systems are equivalent because they have the same solution set, namely 6 minus x3 minus 2 minus 1.5 x3 and x3, where x3 can take any arbitrary real value. The solution set of a system of two linear equations in two variables. The examples that we discuss here. So finding the solution set of a system of two linear equations in two variables is easy because it amounts to finding the intersection just geometrically. If you look at of two lines, where do they meet? Where do they intersect? If they do intersect at all. So one example, let us take is 2x1 minus x2 is 3 and x1 plus 3x2 is 5. And if you plot these equations as lines, the graph, of course, of these two lines, of these two equations, the straight lines, and they do meet exactly at one point, namely 2, 1. And a pair of numbers S1, S2 is the solution of this system if and only if S1, S2 satisfies both of these equations in the system. That means this point lies on both the lines. And here what we see that there is only one point, namely 2, 1, which lies on these two lines simultaneously. And therefore the solution set is the singleton set for this system of equations. Another example, let us take 2x1 minus x2 is 3, the same here as the equation was. And here the second equation is replaced. So minus 4x1 plus 2x2 minus 1. And the graphs of these two equations are these lines 2x1 minus x2 minus 3 equal to 0 and minus 4x1 plus 2x2 equal to minus 1. Now these lines are parallel and these do not intersect at any point. Therefore, this system has no solution. This is, as we can see, that there is no point which lies on both the lines. And therefore, the solution set is empty. Another example, if you take 2x1 minus x2 is 3 and minus 4x1 plus 2x2 is minus 6. The graphs of these equations are the lines 2x1 minus x2 equal to 3 and minus 4x1 plus 2x2 equal to minus 6. And if you see carefully, these two lines are coincident. So they intersect each other at every point. And therefore, this system of linear equations has infinitely many solutions. So we have had examples now where this solution is unique. There is no solution. And finally, this example, infinitely many solutions. So you can just state as a conclusion here that the system of linear equations has either no solution, has exactly one solution, or it has infinitely many solutions. You can see some more examples. So 2x1 minus x2 is 3, x1 plus 3x2 is equal to 5 has exactly one solution, namely 1. And that's what we have already noted here. The other example was that it has no solution, and the third had infinitely many solutions. There is also a term called consistent and inconsistent linear systems of equations. A system of linear equations is said to be consistent if it has either one solution or infinitely many solutions, and inconsistent if there is no solution. The example here we have this 2x1 minus x2 equal to 3, x1 plus 3x2 is equal to 5 is consistent because it has exactly one solution. That was the example 1. Another example 3, that was the last example where the number of solutions were infinitely many, and so this also is consistent. And we also had an example where there was no solution, and that was example 2, and the system therefore was inconsistent. So inconsistent system, for example, 2x1 minus x2 is 3, minus 4x1 plus 2x2 is equal to minus 1 is an inconsistent system of equations because there is no solution to this system of equations. Well, matrix notation. The essential information of a linear system can be recorded compactly in a rectangular array called a matrix. That's how we all introduced in the beginning. So given the system of m linear equations in n variables, so we write all the equations so as follows. So a11x1 plus a12x2 plus a1n(xn) equal to say b1 and so on. And the last mth equation, let us say am1x1 plus am2x2 plus amn(xn) equal to bn. So the variables so here are x1, x2, xn, n variables, and the m number of linear equations. So what we do is we just simply throw away everything and just retain the coefficients, and this then put them in a bracket so that they don't run away. And this beautiful array is a matrix, and this is having m rows and n columns, and call this is a matrix of order m by n. And it's called the coefficient matrix or the matrix of coefficients of the system of equations that we have just now stated. And if we also add one more column to it of the entries that appear on the right hand side of the equal to sign is called the augmented matrix of the system. Well, so just to summarize, an augmented matrix of a linear system consists of the coefficients matrix with an added column containing the constants from the right hand side of the equations. The size of the matrix tells how many rows and columns it has. The augmented matrix has m rows and one more column that makes n plus 1 columns. So this is of order m by n plus 1. M and n are positive integers naturally. If m and n are positive integers, and m by n matrix is a rectangular array of numbers with m rows and n columns. The number of rows we always state first, and then the number of columns. Of course, in this equation, the matrix notation simplifies calculations, and that is why we use matrices and very quickly become very fluent with matrices. So solving a linear system, the basic strategy is as follows. So roughly speaking, we use the x1 term in the first equation of a linear system to eliminate x1 terms in the remaining equations, and then use the x2 terms in the second equation to eliminate the x2 term from the third and onward equations, and so on. Operations to simplify a linear system. So there are three basic operations. So to simplify a linear system, replace one equation by the sum of itself and a multiple of the other equation. Interchange any two equations and multiply all the terms in an equation by a non-zero constant. Just to illustrate this through an example. So let us take an example where there are three equations in three variables, namely x1, x2, and x3. First equation, x1 minus x2 plus 2x3 is equal to 4. The second equation, 3x2 minus 9x3 is equal to 0. The third equation, minus 2x1 plus 6x2 plus 5x3 is 13. And this system of equations, when you throw away everything and just retain the coefficients, then can be written in this form. And the augmented matrix means we shall also include as the last column of the entries that appear in each equation on the right hand side after the equal to sign. So the augmented matrix of this linear system is 1, minus 1, 2, 4, 0, 3, minus 9, 0, minus 2, 6, 5, 13. So it's also a convention, by the way, to read a matrix row-wise. I prefer to do that. The elimination procedure is shown here with and without matrix notation. So what does it mean? That we shall apply the same operations on the system of equations and on the rows of the corresponding augmented matrix and see what is happening. So for the first time, what we do is that add 2 times equation 1 to equation 3. And so you will see that the result of this calculation is the new system of linear equations, namely x1 minus x2 plus 2x3 is equal to 4. And since these operations have been done here, nothing is to be done with the equation 2. So this 2 will remain as 3x2 minus 9x3 is 0. 4x2 plus 9x3 is equal to 21. This is what the equation third has become, because that's what we have done. For this, add 2 times equation 1 to equation 3. So equation 3 has changed. And correspondingly, every time what we shall be doing, throwing away everything, retaining just the coefficients and getting corresponding matrix. So the corresponding augmented matrix of this new system is 1 minus 1, 2, 4, 0, 3, minus 9, 0, 0, 4, 9, 21. And one more operation, that is multiply equation 2 by 1 by 3, that means divide by 3, in order to obtain 1 as the coefficient of x2. The result of this calculation will be yet again another system of linear equations. Since we are doing this operation with equation 2, so first and third equations will stay as they are. 2 will change, of course, the equation number 2 will change. So first equation remains as such, x1 minus x2 plus 2x3 is equal to 4. Second becomes, of course, x2 minus 3x3 is equal to 0. And third remains, of course, same, 4x2 plus 9x3. So observe that here what we have got is that the coefficient of x2 is in this new system is 1. And the corresponding augmented matrix will be 1 minus 1, 2, 4, 0, 1, minus 3, 0, 0, 4, 9, 21. Just take one more step here. So use now x2 in the equation 2 to eliminate now 4x2 from equation 3. And for this, add minus 4 times equation 2 to the equation number 3. And the result will be now. So the first 2 equations will stay because nothing is being done with the first 2 equations. So first equation is x1 minus x2 plus 2x3 is 4. x2 minus 3x3 is equal to 0. The third, of course, changes. Now it doesn't have any more x2. So 21x3 is equal to 21. Corresponding augmented matrix is 1 minus 1, 2, 4, 0, 1, minus 3, 0, 0, 0, 21, 21. Fine. So now you see. So we can also do that in this equation number 3. This is 21x3 is equal to 21. We can make the coefficient of x3 also 1. So what do we do? So we just divide by 21 equation number 3, and the new system becomes x1 minus x2 plus 2x3 is 4, x2 minus 3x3 is 0, and x3 becomes 1. And the corresponding augmented matrix is a beautiful matrix. You can see there was 1 minus 1, 2, 4, 0, 1, minus 3, 0, 0, 0, 1, 1. And eventually, minus x2 has to be eliminated now from equation number 1. But it is more efficient to use the equation 3 in to eliminate now. So what we do here is we eliminate x3 here from the equation number 1. And for this, we add minus 2 times equation 3 to equation 1. So second and third equation will stay as they are. First becomes x1 minus x2 is equal to 2. Second, x2 minus 3x3 is equal to 0 and x3 as 1. And the corresponding augmented matrix now is 1 minus 1, 0, 2, 0, 1, minus 3, 0, 0, 0, 1, 1. We again also can we can add 3 times equation 3 to equation 2. And now what we see is the even more beautiful system of linear equations, because x1 minus x2 is 2, and x2 is 3, and x3 is 1. And the corresponding augmented matrix is so beautiful, you can see now. Here is 1 minus 1, 0, 2, 0, 1, 0, 3, and 0, 0, 1, 1. Good, very beautiful. You still want to make it beautiful, or you want to solve this system? So you can solve this system, then as a solution, you will have x1 is 5, x2 is 3, x3 is 1. And the corresponding augmented matrix of this final system is 1, 0, 0, 5, 0, 1, 0, 3, 0, 0, 1, 1. And just the look itself tells me that the solution is already there. And the solution of this system, and therefore of the original system, because all these systems that we have come across in this process were all equivalent, and so they have the same solutions. Right? So the original solution is 5, 3, 1. So x1 5, x2 3, x3 is 1. However, since there are so many calculations involved, it is a good practice to check the work. And I'm prone to make mistakes, so I always keep on requesting kindly you also verify, and if you come across anything, any discrepancy or an error, please bring this to my notice also. So to verify that 531 is a solution, so we substitute these values into the left-hand side of the original system of equations and compute, and you can see that the results agree with the right side of the original system. So we have verified that 531 is indeed a solution of the given system of linear equations. So the example here illustrates how operations on equations in a linear system correspond to the operations on appropriate rows of the augmented matrix.
Mr. Sharma, can I request? There is a message saying that they all know row echelon forms and everything.
Okay,
so
okay.
You can speed it up a bit.
All right, all right. So just to restate these 3 things. So this is a replacement of one row by the sum of itself and a multiple of another row, and the interchange of 2 rows. And this is called interchange. Scaling means multiple all entries in a row by a non-zero constant. So we say what is called row equivalent if a matrix or the system is obtained by performing finitely many times. So these basic operations on the rows of a coefficient matrix. So in the augmented matrices of 2 linear systems are row equivalent, then the 2 systems have the same solution set. The question of existence and uniqueness of the solutions, of course, is of concern. And the 2 fundamental questions arise are that, is the system consistent? That is, does it has at least one solution? And if a solution is there, is it exactly one? That means, is it unique? So here are the examples that we had already discussed. These examples I will not reiterate here. And in this example, we had seen that there is a solution, and the solution was unique, namely 531. And this is another example here. X1 minus 2x3 is 6. X1 plus x2 plus x3, x3 is 1. 3x1 plus x2 minus x3 is 2. And now we need not perform the operations on the equations of the system. And if we choose to do this with the augmented matrix of this system of linear equations, and then we get back that this is row equivalent to the system, that is 1, 0, minus 2, 6, 0, 1, 5, minus 5, and 0, 0, minus 11. And this, if you convert this into the system of equations, result into an equation, third equation, namely 0 is equal to minus 11. That is absurd. So that means this system has no solution. So when this where we proceed to try to bring the new linear system in triangular form, we are able to find out whether the system is consistent or inconsistent, that means has no solution. Non-zero row or columns and the leading entry. So a non-zero row or a column in a matrix means a row or column that contains at least one non-zero entry. Leading entry of a row means that is the leftmost non-zero entry. Echelon form of a matrix or row reduced echelon form, if it has the following properties. All non-zero rows are above any rows of all zeros, and each leading entry of a row is in a column to the right of the leading entry of the rows above it. And all entries in a column below a leading term are zeros. Row reduced to equivalent form has, in addition to these two more properties, that is the leading term of each non-zero must be 1, and each leading 1 is the only non-zero entry in that column. Equivalent matrix, respectively reduced equivalent matrix is 1, that is in its equivalent form or respectively reduced equivalent form. So you can have just these 2-3 examples to write them in their row reduced equivalent matrices. The following matrix is in equivalent form. So here the squares to denote any non-zero entry. The stars, so they denote that these entries may be 0 as well. The following matrix is in reduced echelon form. This is so because the leading entries are ones and there are zeros below and above each leading one. Here the starred entries may have 0 values as well. So a non-zero matrix may be a row reduced, that is transformed by elementary row operations into more than one matrix in echelon form using this. However, the row reduced echelon form is always unique. So each matrix, there is a theorem, each matrix is row equivalent to 1 and only one row reduced equivalent form. So just to reiterate, if a matrix A is row equivalent to an equivalent matrix U, then U is called an equivalent form of A. And if it is row equivalent to a row reduced equivalent matrix, this is called the row reduced equivalent matrix of this. Pivot positions. So a pivot position in a matrix A is a location in A that corresponds to a leading one in the row reduced echelon form of A. And pivot column is a column of A that contains pivot position. So if you take this example here, as I said earlier also, that the squares denote non-zero entries. Always these are non-zero entries. The stars may have zeros also and non-zero also. And the squares, they identify here the pivot positions. So just an example, so consider this matrix 0, -1, 2, 3, 2, 3, 0, 4, 1, 0, 3, -2. And the aim here is to find the equivalent form of A and locate the pivot position. So if you perform the elementary row operations and obtain this matrix, which is the equivalent form of the matrix A, 1, 0, 3, -2, 0, 1, -1, 2, 3, 0, 0, 0, 17. And the general form of an equivalent matrix here is, now you can see that this is what exactly is this. So you can see that the squares, these are the non-zero entries. So squares are placing here this 1, -1, and 17. And above this diagonal, you can see that these are the entries, star entries. So they could be 0, for example, this, as well as the non-zero entries, for example, this. So here these denote the leading terms and the star entries may have any values. Now squares, they represent here the pivot positions and column 1 and column 2 and column 4 are the pivot columns of this matrix A, the original. So a pivot is a non-zero number in a pivot position that is used as needed to create zeros via row operations. And the pivots in the example 2 were 1, -1, and 17. And you can notice that all these numbers are not the same as the actual elements of A. In fact, a different sequence of row operations might involve a different set of pivots. Also, a pivot will not be visible in echelon form if the row is scaled to change the pivot value to 1, which is often convenient for hand computations. The row reduction algorithm or the Gaussian elimination. So here, of course, is a very efficient procedure for transforming a matrix into a column or row reduced echelon form. So just to write stepwise, step 1 could be that you begin with the leftmost non-zero column. This is the pivot column. The pivot position is at the top. Step 2 is select a non-zero entry in the pivot column as a pivot, and if necessary, interchange rows to move this entry into the pivot position. Use row replacement operations to create zeros in all positions below the pivot. Fourth step is cover or ignore the row containing the pivot position and cover all rows if any above it. And apply steps 1, 2, 3 to the submatrix that remains and repeat the process until there are no more non-zero rows to modify. Finally, the step 5 to obtain the reduced column form, and this last step is performed. So beginning with the rightmost pivot and working upward and to the left create zeros above each pivot. If a pivot is not 1, make it 1 by scaling the operation. So here is an example, and that is shown step by step. So I will not go into these details.
Professor Sharma,
Yeah.
Can I request you to go to
Yeah, please. You are very right.
applications, because we have about 10-15 minutes more.
Okay. So I just say a few words about here. So in step 2 in the row reduction algorithm, the computer program usually selects as a pivot the entry in a column having the largest absolute value. This strategy is called partial pivoting and is used because it reduces round of errors. Then, of course, this solution and the system of solutions, so we shall not go into that. Then existence and uniqueness theorems about the solutions. This is just one thing, that a linear system, as we know, is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. That is, if and only if an echelon form of the augmented matrix has no row of the form 0, 0, B, where B is non-zero. So here these are the columns, so you can see. And you can solve the system of linear equations using a row reduction. And of course, there is another way also that uses vectors. And since we had only talked about 2 unknowns or 2 variables, this can be by writing column vectors. And the equations that can be rewritten in this form. So here, so this is the geometric description of vectors in R2 and likewise in R3. So the vectors are here denoted as column vectors, and they do satisfy some interesting, beautiful properties. And we say that they form a vector space if all these properties are satisfied. An expression of the form C1, V1, C2, V2 plus CP, VP is called a linear combination of the vectors V1, V2, V3, and the coefficients are also called weights. So the augmented matrix it can be written as A1, A2, AN, and B, where AIs are columns and B is the column which is obtained by the rightmost column. And the equivalent of method for this writing this way for Gauss elimination is also presented here. And again, the same existence and solutions. Then the use of matrices, writing the equations in the form of X equal to B, and the properties of these products. So it's all the parametric form. Homogeneous means where all entries next to the equal to sign on the right side are 0. Non-homogeneous means at least one non-zero entry is there. So like that, this is not noted the page number where the superposition plus 2. Of course, the matrices and linear transformations are closely associated. There is a one-to-one correspondence between linear transformation and its matrix with respect to an ordered basis. This, of course, many things can be described in the form of transformations, so reflection through coordinate axis, or the line about x1 is equal to x2, origin, shear, horizontal and vertical projections, and so it's matrices. And it will go on. So let me just state a few things about the applications. As I said in the very beginning, that today there is no subject that is left untouched which does not have its roots or applications in linear algebra. So, for example, if you have electrical engineering, then you have a large system of equations that are obtained for any electric system that is obtained from any building or anywhere. And you have, of course, or say, for example, differential equations. Then also you have applications how to solve the system of, say, for example, first order ordinary linear differential equations, homogeneous form to start with, and that also uses matrices. And say there's nothing as such. And I already have said that this method of Lagrange multipliers that use, of course, the matrices. In fact, your operations or research that can be handled straight away from the point of view. And of course, whenever there is a model, you come across either directly or indirectly to a differential equation, a system of differential equations, and after some assumptions, you convert this to a system of ordinary linear differential equations with constant coefficients. Then it, of course, comes to solving a system of linear equations. So hardly there is anything, and even if you are watching in that or anything, so that also has beautiful applications of eigenvalues and eigenvectors. So I must say that there are plenty of applications, enormous in fact. If you have to talk about, say, coding theory, then you have matrices involved for cryptography, Hill cipher, for example, matrix Hill cipher that also uses matrices. And when you have even, say, linear algebra part in the number field sieve, where number field sieve is basically used for factorization of large numbers. Then also there is a module, there is a part which is dealt by linear algebra specifically to solve the system of linear equations. In fact, there is system of equations, it is basically the system of congruences. And system of congruences, of course, with coprime moduli, Chinese remainder theorem is, of course, a beautiful tool to solve these systems of congruences. And these systems of congruences are needed in cryptography at various levels in many crypto systems. Whenever there is problem that can be converted into a system of equations. So, do you have any specific thing in mind that I should talk more elaborately on that? You can, of course.
Yeah. Probably we can ask the audience in case they would like to ask a question or elaborate on some point.
Well, there is still large material remaining, so but then as we all know that we all have a very, very limited time. The idea of this lecture was this to introduce the subject from the very elementary point of view. So that's what I felt that devote more time on that.
If anyone of the present ones would like to ask a question, please unmute your mic and you can ask the question, because we are not many people now. So you can unmute your mic and ask the question. I think, let me just ask you one question that I think most of the theory, there are probably two aspects of linear algebra. One is the theoretical, other is the computational part of it. So most of the real life applications, they use computational aspects of linear algebra, which is done on mostly on softwares. So what do you think? Do you think those who are using a software should know the theory also well?
Well,
Just asking a very general question.
Although you said that this is a very general question, but I treat this as a very, very specific and honored question, because I would like to recall an incident that once I was called in chemistry department. And I said that, what do I have to do in chemistry department? So they said that you please be a member of the jury. There is some conference in chemistry, and we want that you should come and give your observations in that. And Professor Rana, it was a beautiful thing to see very, very beautiful graphs drawn, because there were poster sessions also, which attracted my sight. And I asked them that your graph is so beautiful.
Yeah.
How did you plot this graph? So he said that I did not draw, sir. This is the GNU plot. So I simply put the values that I obtained from my experimental data. And of course, the computer gave me this beautiful graph. I was bewildered. I asked him that, well, fine, this is beautiful to look at it, but how do you confirm that this is the correct graph? Because no matter how many points you have from your experimental data, if you join end to end, this will always be a broken line. This will never be such a beautifully traced graph. And I remember in my days, we used to have one person, and in fact, a very reputed position was it, called tracer. So the job of the tracer was to trace the graph depending on the data, so that it should pass through as many as points possible. And that was the art that he used to do that. At least there it was visible where the points were and how he was tracing. But here you are blindfolded, you don't know what the machine is doing. How do you know this is correct, that this is the best fit graph or so? That I don't know, and we don't have to know also. So that was a shock. So what I say is, when you have said that is theory necessary, I do believe that to have a good experimental result, a good theory is essential. Unless until there is a good theory, experimental data cannot be validated properly.
So thank you for reiterating that both aspects of linear algebra are important. theoretical as well as computational. To understand computational, one should understand the theory. That's very important. So anybody else has a comment or a question to ask?
Sir,
Yeah, who is it? Please say your name and ask.
sir, this is Dhanushya. If you don't mind, would you say about one thing what I asked now? But this is not what you have thought, but it belongs to linear algebra only.
What is it? Your question.
Would you please say about basis, vector space, something like that?
Oh, you want to ask him to elaborate on the notion of
Yes, sir.
basis in a vector space?
Yes, sir.
Yeah, okay. Professor Sharma,
Sir.
think about basis.
That's very nice. I actually would love to explain all what Dhanushya has asked for. Thing is that it would have taken a lot of time. That's why I skipped all that. But we can go back to that if you want. Before that, okay. So first of all, let me recall what is a vector space. So a vector space, so V is a non-empty set and V is an additive abelian group. That means with respect to addition, this is an abelian group, this is a commutative group. So that means 5 properties are satisfied. So 2 elements can be added and still you get this new element in V. And of course, this is commutative, that means V1 plus V2 is same as V2 plus V1. And associative, that means you add V3 to V1 plus V2 or you add V1 to V2 plus V3. The two are same, so it's associative. Existence of zero means there is a vector called zero vector. If you add this to any vector, it does not change. And for every vector, there is another vector W called the additive inverse or the negate. So then we denote this by minus of V so that the sum of the two is the same zero. The zero is unique. So this is one thing about this. And then we have a field. So a field means it has 2 operations, namely addition and multiplication. So with respect to addition, F is a abelian group. With respect to multiplication, the non-zero entries of F, they also form an abelian group. And the multiplication distributes over addition. That means, so if you have, say, alpha times beta plus gamma is same as alpha beta. The same. So with this, we define a field, and examples of field are, of course, real numbers, rational numbers, complex numbers, and you have all of these as infinite fields, but finite fields are also there. For example, integers modulo, say 2, 3, 5, 7, 17, and for that matter, integers modulo prime is always a field. Now, a vector space V over the field F has the definition as follows. So V is an additive abelian group, F is a field, and there is a map called scalar multiplication. So that takes an element alpha from F, an element V from V, and it produces a new element called the scalar multiple of alpha with V, call it say alpha V, an element of V. So you have with this the properties that alpha V1 plus V2 is same as alpha V1 plus V2, and alpha plus beta V is alpha V plus beta V, and you also have alpha beta V as alpha times beta V. It's to be understood that the operations addition, multiplication, and scalar multiplications from the context from where the elements are coming. And finally, one more property, since F is a field, so 1 is always there. So 1 V, this is an element of V, so which element should it be? So that is, it should be V. So this is the last property it should have. So V is called, in that case, is a vector space over the field F. Now, the examples you can take that Q over Q is a vector space, R over R is a vector space, R over Q is a vector space, but Q over R is not a vector space, as you can take the scalar, so for example, real number and the vector as the square root 2 and it should be in Q, but this is not true. We also call here as a basis, since you wanted to ask about the basis. So first of all, let me define, we say a vector space to be finite dimensional. If it has a set of finitely many vectors, which are linearly independent, that means if there is a linear combination of these vectors equal to 0, then each coefficient must be 0. And these vectors must span linearly over F the whole vector space. That means every vector in V can be written as a linear combination alpha 1 V1 plus alpha 2 V2 plus alpha n Vn. And we call such a set to be a basis for the vector space V over F. Note here that I'm only talking about the finite dimensional vector spaces. So every finite dimensional vector space has a basis. What you can prove is that the number of elements in any two bases are same. And once you have the basis, and if you fix the ordering also of this basis, you can also define what is called the coordinates of a vector with respect to this ordered basis, let us say V1, V2, V2. So you can write this as a linear combination, and this linear combination is unique. So C1 V1 plus say C2 V2 plus C3 V3. And these coefficients, if you just retain and write in terms of a vector, then this is the coordinate column vector of X here vector with respect to the basis B. This is the basis B. So this is what is called as the basis and the coordinates with respect to that. You can have one example, and if you still want, I can elaborate more. So if you have say vectors V1, V2, V, say for example V1 3x2, V2 minus 1 0 1, and X as 3 12 7, and if you say the set V1 V2 as B and H as the span of V1 V2, then you can see the span of this means alpha 1 V1 plus alpha 2 V2, and this will be the vector of the form 3 alpha 1 minus alpha 2, 6 alpha 1 minus 0 times alpha 2, that means alpha 2, and 2 alpha 1 plus alpha 2, where alpha 1, alpha 2 are arbitrary members of the field F. And you can see that this X is in the span, because this can be written here. So this is what is this. So you can see that that is what it is. So suppose it is in the span, that means there exist scalars C1, C2, so that's C1 plus C2 X, that means this. This amounts to basically that's corresponding to the augmented matrix of the system. And if you just obtain the low reduced equivalent form of this matrix, then this is this 1 0 2 0 1 3 0 0. So you can see clearly that C1 is 2 and C2 is 3, the coefficient, and therefore the coordinates here are 2 3, and that's what it is, that X can be written as 2 C1 plus here this is 3 C2, where C1 is your 362 and C2 is minus 0 1, and if you put here this is C1 is 2, C2 is 3, you will get X. So X is spanned by these two, or X belongs to the linear span of V1 and V2. And you can also prove that these two are linearly independent, and therefore this forms a basis V1 and V2, for example, for R2 over R. So do you want more on this?
Darusha, are you there?
Yes, sir.
Okay, so did you follow what Professor Sharma said?
Yes, sir.
Okay, let me ask you a question.
Yes, sir.
You know the plane?
Yes, sir.
Yes. In the plane, how do you describe the plane? By coordinates.
Yes, sir.
What are the coordinates? X, comma, Y.
X and Y.
X and Y, ordered pair. Okay.
Yes, sir.
Right. Now, let me ask you, you must have done this very often. Grade, what are you doing at present?
I'm UG student.
UG student. Okay. So good. So let me ask you, given a vector 2, 3, you can write it as a combination of two vectors, right?
Yes, sir.
0, 1. Is it okay?
Sir.
A vector, for example, with coordinates 2, 3, 2, comma 3 can be written as 2 times 1, 0 plus 3 times 0, 1. Is it okay?
Yes, sir.
Yes. Now, so it's not important. 2 and 3 are not important. You can take any x comma y. X
So
comma,
you are saying that we can write it as a sum of two vectors.
yes, 1, 0, 0, 1. Good. Now, can you drop any one of them? Can you write every vector in xy in terms of 1, 0?
Yes, sir. Then I could multiply with some constants.
Yeah, but then
Then I could draw it with a perfect direction.
no. What I'm asking you is, if you are two vectors 1, 0 and 0, 1, right?
Yes, sir.
If I take only one of them,
No, I couldn't draw, sir.
you can't draw. So both are required,
Yes, sir.
right? So
Yes, sir.
1, 0 and 0, 1 is a minimal set of vectors in R2 which give you everything in R2.
Okay, sir.
Agree?
Yes, sir.
So that is what is called a basis. It's not
Okay,
1,
sir.
0, 1. Any two vectors in R2 which give you every other vector as a linear combination, and you cannot drop any one of them, will be called a basis. Okay. So I think
Okay.
let us ask some other questions from somebody. Anybody else would like to ask a clarification or a doubt or something to be explained by Professor Sharma? Yes. You can unmute your mic and then ask the question if you want to ask. Okay, if there are no more questions, I think it's already around 6:30. So let me thank Professor Sharma for sparing the time and explaining the elementary things to the audience. And I also wish that we had more time for some serious applications. I know you have a lot of things to say about algebra. Yeah. So let me thank him again. And let me thank you all for showing interest in this lecture series. Take care and be safe. Okay. Thank you.
So, well, sir, thank you very much. I'm extremely grateful to you for this interaction meeting, and I am equally grateful to all the participants, and particularly the young and the younger ones most I like to interact with. Of course, I look forward to a time, I think the golden time we come back, in which we shall be meeting people face to face. And of course, that will be the most enjoyable time that we are looking forward. So thank you very much once again for everything. Okay, thank you, sir. Thank you. Have a
Thank
nice
you.
time. Have a good
Thank you. And all of you take care and be safe. Thank you.
Okay, sir. So I leave the meeting.
Yeah, please.
Thank you.